Welcome. So we're going to get into digital signatures. This is something that I noticed a lot of you on your midterms wanted to talk about authentication. The truth is, all of our symmetric methods and so forth actually haven't involved any authentication processes. This all comes down to digital signatures. And how do we utilize digital signatures to kind of understand these things better? So I'm going to introduce you what are digital signatures, and I'm going to give you the most basic example, which is an RSA digital signature. Honestly, this is not the most common one that's out there. We'll talk next in the future about El Gamal's digital signatures and actually what's called the DSA, the digital signature algorithm, which is the most common. And later on, when we introduce elliptic curves, we'll talk about elliptic curves, not only cryptography, but also their digital signatures. So just to understand, let's get to digital signatures and why they're important. So I want to talk about something that I don't know if you even know about. It's the most basic idea about digital signatures that most textbooks and everything refer to. It's known as writing a check. Um, you might have a checkbook. They're very rare now. I paid all through my undergrad. I pay my tuition. I pay my rent. All those things with a check because there was no such thing as this auto deposit and transfer stuff. I had to literally write checks. They wouldn't take credit card charges. They were going to have to need a physical check. And so when you have a check, there's a couple things. One, a check is a tangible object. It's a physical object, similar to a dollar bill that authorizes the transaction. It is a signature that confirms the authenticity. So my signature is what confirmed it. And if there is a case of alleged forgery, a third party would actually be brought in to look at my signature compared to the signature on the actual thing. Now, even though every time you sign a document, it looks a little bit different, because even like right now, I mean, I have something in front of me just to illustrate. I'm gonna sign real quick on the screen. You all can see my signature. So if I was to sign two times in a row, there's not a lot. Even if I do a third time, there's always some slight differences in every time we do these things. I know my signature's gotten worse over time. Um, Probably blame it on the fact I'm a doctor. So signatures, though, there is little subtleties like how I do certain loops of certain letters. There's a consistent process. When you sign most checks, most people are very, very consistent. And admittedly, I'm writing right now on a digital pad rather than actually doing on a physical hard surface like I would normally with a normal pen. And the feel of paper and the resistance of paper is different. So there's a lot of little things. The way ink pours out, there's a lot of details that a third party person can look at. Also, this gets into a different idea, and that's the fact that a check is unalterable or alterations can be easily detected. So let's say I give you a check for $100 and you go use whiteout to change it from 100 to 1,000. Well, that's an easily detectable thing if it's filled out correctly and all these other things. I actually had to go through how to fill out checks in high school as part of one of my finance classes because that was to prevent these sort of things. So we want these something that's unalterable, or if you do alter it, it can be detected and then recognized as this isn't real. And then last but not least, a signature is part of the actual check. It cannot be easily removed or reused. So I can't be like, I can take your signature, I can copy it, and then I can slap it onto a new check. Boom, boom, boom. It should be something that's actually physically part of it, and thus it is hard to remove it. So when we have all these mechanisms, here's a question. How can we define this for signing a document digitally that's similar, analogous to these characteristics? So we want something that's tangible, something with authenticity, something that can be verified by a third party, it's unalterable, and it is cannot be reused. Well, what we do is we refer to those same properties as not these. It's unforgeable. So again, something tangible. We'll get to what each of these mean. It's can be checked as authentic. There's no repudiation. I mean, there's no doubt about its veracity. It is tamper proof. You can't mess with it. You cannot reuse it. So suppose that S wants to send a message to R. They're going to do a signature, which is really, again, just a function. That's why we have all these function ideas. I'm going to have something that somehow is going to deal with myself, something to do with myself, and the message. And it's going to create this. Now, let's talk about each of these things. Unforgeable. That means it's difficult for anyone but S to produce the same signature. Now, key note here. It says difficult, not impossible. The truth is, even with physical checks, there are ways to forge things, and many of them were very difficult, but people would get away with them nonetheless. Authentic. R can verify that S signed a document. In other words, if I send you my signature, you can verify that it is my signature. Repudiation means that I cannot deny producing my, so I can't like send you a check, sign it, and then claim that I didn't sign it. That's part of the repudiation. And that's a benefit, especially when we start talking about e-commerce. This is really important that I can't take back something. Tamper proof. After being transmitted, M cannot be modified. So the message cannot be modified, or the signature cannot be modified. And finally, reusable. The signature cannot be detached and reused for another message. So it is unique to each message. It's not like I'm going to use the same, I might use the same algorithm multiple times, but I'm not going to actually create the same message. And this is the key part about all this. So let's talk about why this is valuable and how we actually start doing it in generality. So public keys are actually perfect for digital signatures. So in RSA, remember, I would take my message and I would apply K algorithm to it. But if then I apply K inverse, my decryption algorithm, it would give me M. On the other hand, if I actually applied the K minus one and then the K, it would redo it. So let me illustrate this a little bit different. In RSA, we had some N, which was equal to two P and Q, two prime numbers. And we took our message and we raised to an E power. And that would give us our ciphertext, mod N. Our D value was a value such that ED was congruent to 1 mod. Now there was a faster way, but in general, it's mod P minus 1, Q minus 1, which was part of the reason that RSA encryption was dealing with. So this power then meant if I took M to the E power, if I raised that to the D power, it was actually going to give me M mod N. On the other hand, if I took, and remember, this is my ciphertext. So that's one way to think about this whole idea. To flip it a little bit, if I take my original message and I raised it to the D power, if I had raised that to the E power, it would still give me M back mod N. Because raising it to the D power, raising it to the E power are inverse functions of each other. So because these are functions that are inverses of each other, we get this. And that is a critical idea throughout this. It's the mathematical idea is, do I have an inverse function or not? So we have to use things that have inverse functions. So if S, actually, this is generally how digital signatures work. If S wants to send a message to R, one way to do that is to actually sign my message using my private key and then encrypt that. So take my message and run it through my private key and then encrypt that final answer via the public key of the person to whom I'm sending it. They can then use their public key. So just to help illustrate this, if R comes along, so let's call this my signature. Let's call that sigma for signature. So if I took sigma and I applied the inverse function of of R. So in other words, R's decryption, that would end up giving me M the KS inverse. But if I then took this value and I then applied the KS function, which is my public key. So see, my private key is still hidden. No one knows what it is. But my public key is available. If someone took my public key and applied it, then these two unlock each other and it just gives me M. So we're applying these functions to help ourselves unlock and undo these things. Now, something to note about this is that often what we do is that's supposed to be hash. We don't actually often use R, we use a hash of M. And the reason we do that is because it makes it a much shorter message. When you hash something, you're decreasing the number of bits. Also, if someone else uses the exact same hash function, it can be completely well known. Then I don't have to worry about much else. So often use a hash instead of the actual message. The other thing, though, is the assurance. What does this give R from this exchange? Well, let's think about it. The only way to undo their key is themselves. So they can know that unless someone else has their private key, they can't unlock to get into this interior message. However, this was using my private key. So the only way that someone could have gotten this was if they actually compromised my private key, in which case I'm totally compromised anyways. So both these situations, the only assurance is that unless one of us is actually both of us are completely compromised, no one else can have access to all this information. So R gets the knowledge of the only way this message was. If it doesn't match my M, then we have a problem. So let's go back to those properties. Let's talk about why this has those properties. Remember, this is the message that they're sending. And remember, the 5 properties we want it to be unforgeable. So again, I'm just going to run all you back to the definitions of these things. Unforgeable, it is difficult for anyone but S to produce it. It's authentic, it's irrefutable. I can't deny it. It's tamper-proof and not reusable. So let's talk about each of those for this message. It's unforgeable because only S can use KS inverse, because remember, that's my secret key. It's authentic because any third party can actually take, once I unlock through the outside, if I'm R, once I unlock that and just have that M run through the KS inverse, any third party can apply that and check the M that comes out of that. The repudiation is that only S could have used S inverse, therefore I can't deny that part. Otherwise, I'm saying someone's totally hacked. The only way to say that is someone totally hacked me, and then my whole system's compromised, and we got all sorts of issues. Finally, it's tamper-proof because only R can remove that outside layer of encryption. So once I encrypt it, the only person who can undo it is the person to whom I'm sending it. So it either has to be attacked before I get to that or something along the lines. And finally, it's not reusable. So this signature is based on the message I'm sending. So every time I do a message, it's obviously going to change the signature that's associated with it. So these are how these digital signatures actually work. So let's talk about the RSA digital signature. It's going to be our example. It's actually a very straightforward. It's going to make sense. And I'm actually probably going to I'm going to bake it down a little bit. So let's first review, how does RSA actually even work? So I already kind of did this. Quick reminder, RSA is based on a couple different things. First, in RSA, if I'm Bob, I pick P and Q, which are primes. And then I compute N, which equals P times Q. So that's 1, 2. Step 3 is we choose some E that's between 1 and, I'd prefer it between P minus 1, Q minus 1, because that's just going to be the best way to work out. And then we find D such that DE is congruent to 1 mod P minus 1, Q minus 1. Now, another way, remember, the faster way to have done this was that it was congruent to 1 mod P minus 1, Q minus 1, divided by the greatest common divisor of p minus 1 and q minus 1. Because there is, since p and q are going to be large primes, at least 2 is going to be in there. I can at least cut that number in half, make it much smaller, makes my Euclidean algorithm go way faster. All those wonderful things. This is going to be the kind of the idea that we actually really like about that. So I'm just going to erase that little bit, but that is the idea. Now, there's two things that I stick out there in the world. From all of this, I have my public key, which is N and E. And I have my private key, which is D. On the other hand, Alice over here, so if Alice wants to send me, what she does is she takes M. Well, first up, what Alice needs to do is she needs to look me up in a directory and she has to see what I got. So one, she has to look up Bob. And by that, I mean there's directories out there that I can look up Bob, and she gets N E. So now she computes, and I don't want that. The ciphertext, which is her message to the E power mod N, and then sends C to Bob. Now here's the really cool part. Bob can take that and easily decipher it because, again, as a quick reminder, Bob, what he can do is simply C to the D mod N, and that will actually give him back the message itself. So Bob can go through this. He can easily find all these values. It's great. It's wonderful. We can look it all up. The key thing here is I'm taking things and I'm raising them to powers. And the way they undo them is raise them to the opposite power. That is essentially their inverse mod, the p minus 1, q minus 1. So how does that work for RSA signatures? Well, it actually starts very similar. Bob has a public key. We're going to call it N1, E1, because they're both going to have public keys, and a private key D1. Bob wants to sign a message M that he is sending to Alice. So he looks up Alice's key, which is some other N and E. We'll call them N2, E2. I'm using subscripts to make these a little bit different. Now, we know that he can encrypt that by taking his message M and raising it to the E2 mod N. And that will give him his ciphertext. Now, Alice can easily do the ciphertext. However, so that's one thing he's going to send to C. The other thing he needs to do is now he needs to add his signature, which is actually this ugly, nasty process right here. So he's going to send S, which this wrapped it around. I'm going to rewrite this down here. So essentially what it is he's going to take his message and raise it to his power, mod his. So this is Bob's mod. And this is Bob's private key. And then he's going to take that whole thing and he's then going to raise that to Alice's public exponent. And then take all that mod her mod, Alice's mod. Why? Because these are really the two different functions. Each one is a function. We're running it through an exponent and then a mod. Exponent and then a mod. That's the function that we're operating in here. And when he does this, he will get an output that is the signature. Now, that is a wonderful, easy way, especially if the two N values are relatively close, if they're both massively huge, which is pretty typical in the world. And now Alice has the key, so she can simply raise this whole nasty thing to the D power, which will give her back the inside portion right here, which then she can then look up Bob's public key and use his public key to actually unlock that and verified M. So that is the idea behind how this works. Again, Bob is using all these things. And then Bob would send his signature S and C on. So let me show you how this works. Let's do an example. Except we're gonna take Audrey. I'm gonna change letters just for a little bit, names. Instead of Alice, I'll give you Audrey. And she's gonna RSA modular this massive ginormous thing, which obviously it's odd. We don't know what it factors. That's kind of hard. But the modulus is going to be public. So both of these values right here are going to be public. So that mod is public and the encryption exponent is public. So both of these are well known. Zeke can look them up. She's going to send a Zeke. I know, instead of using Bob, I'm getting crazy here. I'm using a Zeke. And she's going to send the message, "You are cute." I know it's a little late for Valentine's Day, but we're going to go with that message anyways. And she wants to put a signature on it so that Zeke knows it is her and not one of his friends. Because if you just got the message, "You are cute," how does he know who it's coming from? So she's going to put all this on there. Now, Bob's going to get the message. And to get the message, she has to encrypt it. So she takes the message, "You are cute." And again, each of those letters, base 26 turns into a number from 0 to 26. She then can take that into a base 10 number, and that will give us this number right here. And so, which happens to be smaller than my modulus, which is required. And now she can convert that. And this is what "You are cute" looks like if you turn it into a decimal form. That means I took Y and Y turned into, let's see, what's that, 24, but that's 24 times 26 to the 8th power, and then O, etc. Change each of them. She then uses her decryption signature, which ironically, if E is 23, the decryption for this whole nasty thing is this value down here. So this thing right here is her decryption power. So she takes this message, she raises it to her decryption, her mod, her N, and she's going to send this to Zeke. So she's going to send this signature, just the number, not the mod M, just the signature. And she's going to send this number right here to Zeke. All right. So Zeke is going to get those things from her. At this point in time, if Audrey's sending this, obviously she never encrypted X. And the reason I'm doing that is just say, let's suppose she doesn't really care if anyone reads her message. She's open about her feelings for Zeke, but she doesn't really care if anyone else. She's more concerned. So she's less concerned about him encrypting that and misreading it than actually just and knowing it's her. So Zeke, he can translate this message into readable text pretty easy. And then once he gets these like "You are cute," he's like, it's my buddy's messing with me. So he looks up her modulus, which is 23. He takes her signature, which is this giant thing, and raises it to 23 powered mod M. I'm not going to type out what M is. That's a massive number. But he gets this. And as a quick reminder, this is X. So because this is exactly X, Zeke knows that Audrey had to send it. And that is the punchline. So again, what we are doing for RSA is we're simply applying the RSA, but instead of applying my public, because remember, when I put out a public key, that's for other people to send to me. This time I'm going to take my private key. I'm going to encrypt it, so to speak. I'm using finger quotes. Using my private key, then I'm going to use the person I'm sending it to's public key to encrypt that and send it on as a two-part. So this is a two-part message. It actually is a message and a signature, separate packages we utilize and so forth. All right, hope that gets you started. Let me know what questions you have. Good luck.